Hi everyone, Kamran Nouri here. This video is the first of the series of lectures related to momentum, conservation of momentum, and collisions. Here are the list of topics covered in this video. First, we introduce linear momentum for one particle. Then we extend the definition to a system of particles. Then we talk about Newton's law in momentum form, from which we conclude conservation of momentum for a system of particles. And finally, at the end, we talk about different types of collisions between two objects. We already talked about center of mass and velocity of center of mass that is relevant to this part. I review with you 1 over the total mass of the system times sum of all mi di. And this was what we had before. But now I want to introduce momentum. A linear momentum for a particle that has a mass m and moves at velocity v, we define linear momentum denoted by p, and is defined by just multiplication of the mass times its velocity vector. Because velocity is a vector, you multiply by a scalar, you get another vector. That vector is momentum. It's very important. Momentum is a vector. It's not a scalar. And its unit is kilogram meters per second squared. We don't have a name for it. We just call it kilogram meters per second. That's the unit. And this turns out to be an important quantity. And I'm going to show you how and why. Just starting from Newton's law. If we look at Newton's law, which is F equals ma, m dv over dt. If F is constant, we can say delta v over delta t. Then this mass is a constant, can go inside the derivative, right? So F becomes d of mv over dt. So that means that the force is change of this mv quantity that we call it momentum. So force is rate of change of momentum. dp over dt is called Newton's law in momentum form. All right? So now, if you have a system of particles, what happens? If you have a system of particles, each one is moving, let's say these are different particles of the system, is M1, M2, M3, and in general Mi is moving, each one is moving at one velocity, V1, V2, V3, and so Vi. Each one has a velocity. If you add all the velocities times masses together, if you find the total momentum, P total, which is sum of all the masses, Mi, times its velocity, that is the total momentum of the system, which is a vector. If we multiply each velocity by its mass, and then add them together, right? That's the total momentum of the system. And look at this. This total momentum of the system is equal to the momentum of center of mass. And then, if you write Newton's law for each particle in momentum form, see what we get. You can write F1 acting on the first particle is equal to d over dt of p1 as a vector. And the same for all of them, so I can say this is for each one separately. Then if you add all of them, sum of fi is equal to d over dt of sum of pi. So sum of pi means total momentum of the system, right? So, and remember, sum of all the forces, because internal forces cancel each other, we can say F net external is equal to rate of change of P total of the system. This is Newton's law for the system of particles in momentum form, right? This is Newton's law in momentum form for system of particles. Okay, so we can write the same as this for the whole system. And this is where momentum becomes interesting, because the net external force is equal to the rate of change of the total momentum of the system. And now, see what happens if the net external force on a system is 0. What can you conclude? If the net external force on the system is 0, what do we get? What can we say about the momentum? Yeah, the derivative is 0, means that the quantity is constant, right? The derivative of total momentum is 0 if the external force is 0. Therefore, the total momentum is conserved. That's conservation of momentum. Very simple. So if F net external on a system is 0, then P total for the system is conserved. So if you have a number of particles, total momentum, which is sum of MI/VI, is constant. Means that whenever the particles interact with each other, as long as there's no interaction with outside the system, we have total momentum MI/VI prime after equal to total momentum before. So this is total P before. This is total momentum after. After each time interval, each collisions may happen, or they interact with each other. Whatever happens, as long as the F net external is 0, the total momentum of the system is conserved. Especially for two objects, when the two objects collide with each other, sum of the mass times velocities before collision is equal to sum of the mass and velocities after the collision. That's called conservation of momentum. And that is why momentum is very important. And as you see, there's nothing more than Newton's law here, but we're looking at this Newton's law and interaction of particles or objects in a different way, just from the point of view of momentum. Remember, in the last couple of chapters, we talked about work energy and conservation of energy. That also wasn't anything new from Newton's law. We were looking at Newton's law in a different way, looking at energies instead of forces. Now here, we look at momentum instead of forces. So it's, again, the same kind of mathematical trick to look at the phenomena differently. For example, if two things collide, and there's a sharp force between them, and we don't have much information about the forces, but we don't need to, because we can just look at the total momentum before and after, and we say that it is conserved. And you heard about the collisions, different collisions. Sometimes they call elastic collisions, sometimes they call inelastic collisions. For example, if you throw a ball at the wall, it collides with the wall and comes back. Depends on whether it comes back at a lower speed or the same speed, or if it sticks to the wall, we have different collisions. So I'm going to classify the collisions, and this is our main equation here, with momentum defined by that, which we call conservation of momentum. All right, so from all this story, what you need to take away is that the momentum that's defined like that for a system of particles, momentum is conserved, especially before and after collision. Right? let's say, collision, especially between two objects. And we want to see what is the difference between elastic collision. Sometimes we also call it completely elastic. And then we have inelastic. And then we have completely inelastic. What is the difference between all these? So first, from the total momentum point of view, P total, for elastic collision is conserved. When you have elastic collision, total momentum is conserved. And also, kinetic energy total is also conserved. For elastic. And then in terms of rebound, when the two objects hit each other and rebound, their relative speed after the collision and relative speed before collision is the same. It's the same as something thrown at the wall. It comes back at the same speed. If it comes back at the same speed, the relative speed is the same. So V relative after over V relative before. And the ratio of the relative velocities before and after, this is the same. The ratio will be 1, bounce with same relative speed. The example of that is when you throw a ball at the wall and has elastic collision, it rebounds with the same speed as it went in. The relative speed is the same. So, example, ball bouncing from wall. Bounces with same speed. Now, what about inelastic? For inelastic collision, momentum total is also conserved, is always conserved. Total momentum is conserved, but kinetic energy is not conserved. Not conserved. Or some lost. Some kinetic energy is lost. And then relative velocity before and after, the after is smaller than before, so it's less than 1. They bounce with smaller relative speed. And for the example of a ball bouncing from a wall, it goes at speed v, like 20 meters per second. It bounces back at 15 meters per second. Bounces with less speed. What about completely inelastic? In completely inelastic collision, the total momentum is still conserved. You see, when I was showing that conservation of momentum, it didn't depend on what happens after. It just, Newton's law says the momentum has to be conserved. But kinetic energy is not conserved. And maximum kinetic energy that can be lost is lost. So you say here, maximum kinetic energy is lost. Not all of it is lost, maximum is lost. And then, what do you think about this? Relative velocity after divided by relative velocity before is 0. Means that objects stick together after collision. And here, for this example of ball bouncing from a wall, it doesn't bounce back, it sticks to the wall. Okay, so this is classification of collisions. Any questions? Is that understandable? We have elastic, inelastic, completely inelastic. Usually, we talk about this elastic collision or completely inelastic collision. This ratio of the relative velocity after divided by before, that is less than 1. It is somewhere between 0 and 1. And that actually shows the percentage of elasticity. If they say, for example, a collision is, let's say, 60% elastic, means that relative velocity after collision is 60% of the relative velocity before collision. So with that, it's all kinds of collisions are now, I think, covered. All right? Now we're going to have what happens first in this, because this is the simplest one. Because when two things collide, if they stick together, we only have one final velocity. It's easy to solve it. We have one unknown. But when we have elastic or inelastic collision, but not completely inelastic, we have two velocities to solve for. And that makes it harder to solve. But it is doable because you can form two equations, two unknowns, one with kinetic energy, one with potential energy, and solve for two velocities. So this is classification. Now I'm going to talk about completely inelastic collisions in one direction, one dimension. We can have also collisions in one dimension. We can have two dimension. So different collisions in one or two dimension. That gives you several different scenarios. So I'm going to talk about 1D collision, and first completely inelastic, and then talk about elastic collision. And then we're going to talk about this system, which is called Newton cradles, and I'm sure most of you have seen it. Why, when you do this, one of them hit here, only one of them on the other side goes. And if two of them, more interestingly, if two of them here, two of them go on the other side. Why? We're going to consider, because these are almost elastic collision, we can consider elastic collision and then explain this phenomenon. All right? Thanks for watching. Please see my next video for examples of collisions and explanation of Newton's cradle.